Good day, grade 10s, this is yes. Grade 10s, this is just a discussion about the work that you are writing the second paper on, which is the chemistry part of your paper. Right, so in this part, we will first be focusing on all the chemistry work which you mainly have done in the first term and a little bit of it in the second term at the end of the term. Right, so we are going to look at matter materials, macroscopic properties, kinetic molecular theory, the atom, the periodic table, chemical bonds, and particles of which substances are made up of. Okay, and we are going to look at chemical change, physical and chemical change, and the writing and balancing of chemical equations. So many of these things you have already discussed in your grade 8 and 9 year, and it was just a little bit further on, especially regarding the chemical bonding of the work that we did new in this year. And then also things like writing of or changing in the appearance of a substance when it is heated, the kinetic molecular model. It's also work which you should be familiar with since last year. Now this paper 2 that you are going to write will be written on the 5th of June, and it's a 1.5 hour paper. It consists of section A, which are multiple choice questions, 5 of those, each worth 2 marks. And then section B is a more structured questions where you must really have a look at the marks allocated to each question so that you know how much facts you should write down. Usually a question starts off with asking some definitions, and each definition is worth 2 marks, and that is important that you do not describe something in your own words when a question asks for the definition, but you should know your definitions by heart. And then it slowly builds up, and increasingly it becomes more difficult as the questions on one topic is being asked, and then the final question is usually a level 4 question, which is a question which you have never seen before and where you have to apply the knowledge that you gain from this topic. So this will be worth 65%. But if you work hard, if you learn your definitions, and you really put in the hours, you will see you can easily have a 50% for this paper. Now, if you look on the screen now, you will see there you have the periodic table. And the periodic table then is, how shall I say, it's one of the documents that you will receive each and every chemistry paper. You must just be able to use it. So hydrogen will always, each and every chemistry paper appear on the left-hand side top and helium on the right-hand side top. It will always have the same shape, and it has this specific shape because elements are arranged in vertical columns called groups, and there are 18 of these groups, um, starting from the left-hand side with the metals, group 1 being the alkaline metals, group 2 the alkaline earth metals. Then from group 3 to group 12, you have what we call the transition elements, where elements have some properties that sometimes they react for something like iron, for instance, will sometimes react as like the elements of group 2, sometimes as if it's an element of group 1, and it can even react as if it's an element of group 3. And it depends on the moisture and the heat and all those surrounding factors that influence the reaction between iron and oxygen. It does not always give you rust as you see when it forms in the outside, when a piece of iron is exposed to all the elements that we experience on Earth. Okay, So then we carry on with the elements in group 13, and from 13 on it slightly becomes more and more non-metallic. You will see there is a zigzag pattern starting between boron and aluminium. It ends up here between LV and UUS at the bottom right hand side, and all the elements to the left hand side is the metals, so they are the big group on this periodic table, with the exception of hydrogen. Hydrogen is always an element of that it appears in group 1 because it only has one electron. So that electron is also its valence electron. The other elements on the right hand side of this I call it a step ladder, or sometimes it's called a zigzag pattern. They are the non-metals. And you will see you have 7 of those in yellow, and they are called the metalloids, and the metalloids are the elements that sometimes react like the metals, and other times, depending on temperature and circumstances, as if they are non-metals. So you will not get this specific periodic table, because on this specific periodic table, you will see there we have the names of the elements written in the blocks, and that will not be the case. So you must make sure that you know the symbols, and especially the first 20 elements, you must know these symbols, and then the ones that we most commonly use, like cobalt, iron, nickel, copper, zinc, silver, mercury, gold. I think they are the most common ones that we make use of most of the time. Right, so here you will see, you can clearly see the zigzag pattern here on the right hand side, showing you which elements are the metals and which are the non-metals. Right, now if we refer to the term valence electron, we refer to the elements, the electrons of the element of an element that is in the outermost position furthest from the nucleus, if I can put it that way. So around the nucleus you find energy layers, and in those energy layers there are a certain number of electrons, but there's a pattern. The first energy layer, called the K level, can have a maximum of 2 electrons around it, and if that energy layer is filled with electrons, the rest will overflow to the second energy layer. And that one further on, they can have a maximum of 8 electrons. So we refer to the octet rule that is applied so that elements try to have a complete outer layer of 8 electrons before they appear in nature. Now, all the elements of group 1 has one valence electron. So they are like a family, having one specific property that stands out. And this is that in the outermost layer, they have only one electron, and that is their valence electron. The elements of group 2 have 2 valence electrons in their most outer layer. And then we move on to group 13, and now you ignore the one in front of the 13, 14, 15, 16, 17, and 18, and you will see elements of group 13 have 3 valence electrons, group 14, 4, group 15, 5, group 16, 6, group 17, 7, and all the elements of group 18 except for helium has 8 valence electrons. Now, the reason why helium is considered to be part of the noble gases, which are the elements in group 18, is because it also has a completed outer layer, because it has only 2 electrons, and those 2 electrons appear in the first energy layer, and then it's completely full. So the others needs 8 electrons to be completely full. So the noble gases, the elements of group 18, are chemical unreactive elements. And there are 4 groups that have special numbers. It's the 2 groups on the far left-hand side and the 2 on the far right-hand side. So as I've said, group 18 is the noble gases, and next to it, the group that has 17, group 17 having 7 valence electrons, they are known as the halogens. For left-hand side, elements of group 1, alkali metals, elements of group 2 having 2 valence electrons, they are called the alkaline earth metals. Right. Now, if we refer to the reactivity of metals and we look for trends on the periodic table, then you will see on the left-hand side, we have the indication of reactivity change of the metals, and on the right-hand side, the non-metals. And their trend is directly opposite of one another. So you will see at the top of this periodic table, you have an arrow pointing from the right to the left, which indicates that the elements, the more they lie to the left-hand side, the more reactive they become. So if you look at the 2 elements, sodium and magnesium, in period 3, the third horizontal row, then sodium is the element that lies more to the left. So it will be a more reactive element than magnesium. And if you look at the elements and you compare elements in group 1 with one another, the lower you go from the top to the bottom, the more reactive the element becomes. So regarding the metals, francium on our left-hand side corner at the bottom is the most reactive element. The opposite works with the non-metals, but now remember, we now ignore the elements of group 18 because they are chemical unreactive. So the most reactive element in group 17 is at the top. It is francium. So reactivity for the non-metals increases from the left to the right and from the bottom to the top. So fluorine is therefore our most reactive element in this group. Now you must remember ionization energy, electronegativity, as well as electron affinity, those 3. The brown one at the top, the brown one at the bottom, and the purple one second from the top. Those 3 have the same trend, increasing from left to right and from bottom to top. And then atomic radius opposite to that. Atomic radius gives you an indication of the biggest atom that you will have is francium here at the left-hand side bottom. So it increases from top to bottom and from the right to the left. These 2 diagonal ones, metallic character and non-metallic character, is really not important here. Right. Structure of an atom you should be familiar with since grade 8. Protons and electrons are equal, and it corresponds with the atomic number of an element. The atomic mass minus the atomic number gives you the number of neutrons, and usually for the first 20 elements it is plus minus the same, or maybe 1 or 2 more. But if you go to the larger numbers from 84 and so on, you get the elements that are naturally radioactive elements, and that is because there is such a great difference between the number of protons and electrons. And we say these elements are then the elements that, or the function of the neutrons is that they stabilize the element. Okay. Right. We also can divide the periodic table in an S block, a D block, a P block, and an F block, depending on where the valence electrons lies. S orbitals are round-shaped areas where you would find electrons, and they can only be 2 electrons in an S orbital. And in each of the levels K, L, M, and O, we find 1 S orbital. The p orbital starts from the second energy layer, and they consist of 3 level 8 figure spaces in 3 dimensions, and they can have a maximum of 6 electrons in those 3p orbitals. So the 6p orbitals, or 6 electrons in the 3p orbital, starts from the second layer, plus there is an s orbital. So that's how we can explain for the first 20 elements. We can relatively accurately describe the distribution of electrons using orbitals having certain space to have electrons in a specific orbital. Now, we are not doing d orbitals or f orbitals at school level. Just know about it, and that is how we can explain the spread of electrons in much bigger elements. If we refer to ion electron configuration, our example here makes use of a magnesium, element 12, having 12 protons in the nucleus, 2 electrons in the first energy layer, 8 in the second, gives you 2 plus 8 is 10, 2 electrons in the outside layer. So therefore, magnesium atom will be an element of group 2 because it has 2 valence electrons, and it will be in period 3 because it has 3 energy levels. Now, the metals are the elements that during a chemical reaction, they donate their valence electrons. So therefore, a sodium atom donates its 2 electrons, releases it. Now that whole layer disappears, and you will see now it looks like this. Now we have still 12 protons in the nucleus, but only 10 electrons around it. So we have 2 more protons, and now where an atom is a neutral particle, as soon as electrons are gained or donated or released, then there's the number of protons and electrons are not equal anymore, and then there's a charge on the particle that now has formed, and this is called an ion. And in the case of magnesium, it will have now a plus to a charge. So the elements of group 1 will have a plus 1 charge, elements of group 2 plus 2, elements of group 13 plus 3, group 4 plus 4 or minus 4, depending on what they are reacting with. Elements of group 15 has 5 electrons, so the non-metals gain electrons, so they have place to add 3 electrons. They can accept 3 electrons, then they have 8 electrons and a complete outer layer. So 3 more electrons means the charges of the ions of the elements of group 15 will be minus 3, group 16 minus 2, group 18 minus 1, and group 18 0 because it's chemical unreactive. If we now look at the difference between the notation, S&P notation, or electron distribution, then we do it according to the orbitals, only using S&P orbitals. You have for the atom of magnesium, you have to place 12 electrons. But for the magnesium ion, because it released 2 of its electrons, only 10. So the small number indicates the 2 electrons in that space. The bigger number indicates the level. So the first energy level has only an s orbital. The second energy level has a s orbital as well as a p orbital. And the third energy layer has a s and a p orbital. So 2 electrons in the s orbital, that's the maximum in an s orbital. So it's 2 plus 2 is 4. The maximum in the p orbital is 6. So now I have 10 electrons. So 3s has space for 2 electrons. So this is how the magnesium atom looks. The magnesium ion has 10 electrons. So this last 3s2 falls away. Can you see? So now it's only 1s2, 2s2, 2p6. 2 plus 2 plus 4 gives you 10 electrons. 2 electrons has been released. We look at chemical bonding. Remember, there are 3 types of bonds. When a metal bonds with a non-metal, we refer to ionic bond. When non-metal bonds with non-metal, it's covalent. And when it's metal with metal, it is metal bonding. With ionic bond, there's electron transfer from the metal to the non-metal. In covalent bond, sharing of valence electrons. And with metal bond, atoms are just closely organized. Um, for the transfer of electrons, as I've said, it's from the metal to the non-metal. So the metal forms a positive ion, or other words, we call it an cation. And then the non-metals accepts an electron, and then we say they form an anion. And opposite positive and negative ions will attract. Sharing of electrons, example at the bottom, nitrogen, 5 electrons because it's an element of group 15. It has 5 valence electrons, 2 are paired and 3 are unpaired. So 3 hydrogen atoms overlap with each with their own electron, and they fill up each other. So that nitrogen now has access to 8 electrons in its outer layer, and the hydrogen has access, each atom, to 2 electrons in its outer layer. So they share, they overlap and they share. Here on the right hand side, we have the metal, and the metal bonding is where that is typical of metals, that the particles are very closely, densely organized, and then the protons in the nucleus takes in structural positions, and the electrons are moving like bees in a hive the whole time in between those structured nuclei, positive nuclei. So we refer to this motion of the electrons, we say they are delocalized valence electrons, and that makes for the metals to be good conductors. Right, here the question asks which of the following is found in group 3, period 2. Now you can think group 3 can be in this group here, or it can refer to the old group 3. Nowadays we would write group 3, the Roman 3, and then in brackets 13, for instance. But in this case you would have seen here at the bottom only the upper part of the periodic table is given. So therefore you can't see what is in this group 3. So that's why you know it should be one of these two. And the only one there is then boron A. The molecular formula of sodium carbonate, sodium, element of group 1, +1 charge. Carbonate is one of our polyatomic radicals. You must know it's CO3 2-. The pluses and the minus charges should cancel out each other in the final formula. So in order to cancel out the 2 minuses, we must double the sodium ions. So now the formula is Na2, and only one carbonate group because it contributes 2 minuses. So your final formula must not have any charges in it, then it's incorrect, and therefore C was the correct answer here. The next question asks the energy change that occurs when an electron is absorbed by an atom into the gas phase to form an anion, and this is now I'm not sure about this one. It is actually the definition of electron affinity, so I think this is not correct here. So I wouldn't say this is activation energy. Okay, it is C that is the correct answer here and not D. I can unfortunately not remove it. Then here, the number of valence electrons in a neutral phosphorus atom. Here's phosphorus P. It's an element of group 15, which indicates it has 5 valence electrons, and therefore B is the correct answer. The next one. Okay, so let's just, I unfortunately can't go back now. So, oh yeah, I can go back one. Let me just see. Okay, chemical bonds, this is what you need to know. chemical bonds are matter that are composed of particles. We have three types of chemical bonds. It's the covalent bond, the ionic bond, and the metal bond. You must know that the product of a covalent bond is a molecule, and that the product of an ionic bond is actually a formula. It's not formulas, it's actually a formula unit, or you could have said an ionic crystal. Right, next one. Drinking water can best be classified as, and now here water has the formula H2O. It doesn't matter if it is distilled water. If we say water, we refer to H2O. But as you know, water is not always very clean. So water is a compound. That's 100% true, with the formula H2O, two hydrogen atoms combined covalently with one oxygen atom. So B is the correct answer here. It says drinking water. So you could have reasoned here that drinking water should indicate pure water. So then I would say it should be homogeneous, but it's not necessarily that it is homogeneous. Okay. But then on the other hand, if it's not homogeneous, it would be heterogeneous. So I'm just here. If you think drinking water, it should be pure, and water is a compound that B and C, but I would say that B is the most correct answer. Yeah. Right. Yep. How many protons, neutrons, and electrons are in a sodium ion? Na plus. The atomic number is 11, so it has 11 protons, which means it can either be A or B. 23 minus 11 is 12, so it should have 12 neutrons, so it's still A or B, but it's a sodium ion with a +1 charge. So this means that it had 11, in atomic form it had 11 electrons. But it donated one of its electrons, the valence electron. So that is how it became Na plus. So that means that B is the correct answer, because the ion will have one less electron. Okay. Next question: which substance would not find would you not find in a covalent bond? A covalent bond is where a non-metal bonds with a non-metal. Chlorine, hydrogen, and iodine are all three non-metals, so it can only be A, where you will not find a covalent bond. Right, which statement does not apply to an ionic crystal? An ionic crystal, think about sodium chloride. It has a high melting point. It is hard and brittle. Electrons are transferred from a metal to a non-metal in an ionic bond. So these three are correct. So D says forms a molecule made up of atoms. And remember, I said now earlier that a molecule is formed as a result of covalent bonds. So therefore, the one that is incorrect here is D. Right, here we have an graph. It is a heating curve graph because there's a raise from the left to the right. And every time that there's an increase in the temperature, that is where the kinetic energy is increasing. So increase in temperature goes with increase in kinetic energy. But the two places where there's a flat piece of the graph, that is where the temperature remains constant. So your kinetic energy is remaining constant at those two places. And that is where the potential energy is increasing, and the energy is being used to change phase. So temperature change between A and B, between B and the next point of change, the horizontal part there, that is where at the lowest place, which is here, it melts. Then it is a liquid in the next part of the graph between plus minus 58 to 92 degrees. So then we have water, and then the next flat part of our graph is around about by 92 degrees. That is where the water or this substance is now boiling. and then it changes and it becomes a gas steam, if it's water. But in this case, we don't know that it is water because we're not told that it is water. It just refers to a substance, and then it is in the gaseous phase and it can still increase in temperature. Right, if we look at the next graph, it's similar to the previous one, but here, or no, it's actually the same one, sorry, it just looks a bit different. It refers in question 4 to room temperature. Remember, room temperature is the temperature around about, I would say, on a cold day, maybe 12 degrees Celsius. Here in South Africa, on a hot day, it can be just above 20 degrees, but round about there. That is room temperature. So it means that it will be here. It is 30 degrees at the start when the time starts. So it means that before we started with recording data to draw a graph with, it should have been at a temperature lower than 30 degrees, that the substance would be in the pure solid form. Right, here it changes between A and B, not changes from phase, it increases its temperature and then it melts. Okay, and it melts around about at 58 degrees. Right, so, and then in question 6, the question asks, could the pure substance above be water? Now, water boils at 100 degrees Celsius and it freezes or melts at 0 degrees Celsius. So this substance is melting at a high temperature of 58 degrees Celsius and it's boiling at a lower temperature than 100 degrees Celsius. So this is how we know it is definitely not water. Here we have information about uranium-235 and 238. So it means two atoms of uranium having different atomic masses, and you have isotopes of this uranium. And the first question asks to find the term isotope. Please do not describe what an isotope is. Give the correct definition. It is atoms of the same element having the same atomic number but different atomic masses. Question 2 asks, correctly calculate the relative atomic mass of uranium to 2 decimal places. So you know the percentage of isotopes present. 0.7% means 0.7 out of 100. And 99.3% means 99 out of 100. So the first 0.7% of 235 gives you 1.645, and the second 99.3% times the 238 gives you 236.334. If you now add these two numbers, you get a value of 237.979, and the question says to 2 decimal numbers. So therefore the third number is bigger than 5, so it makes the number 2 place 1 bigger, so it becomes 237.98. And then the question said relative atomic number mass. So remember, if it says relative atomic mass, no unit, just the number. Right. Then question 3 on the same question asks, explain why uranium-238, which is more abundant, is not suitable as fuel for nuclear reactors. And the reason is that in a nuclear reaction, you start with a small action and then a whole lot of chain reactions follow, and that it releases a huge amount of energy. But for some odd reason, uranium-238 does not have the property that it can sustain a chain reaction, and that is why it can't be used in nuclear reactors. Right, next question is about first ionization energy. A very common question to ask is the definition of ionization energy. This is the energy needed per mole to remove the first electron from an atom in the gaseous state. So the first electron is not the electrons closest to the nucleus, it's the electrons that are the furthest away from the nucleus. So to remove the first one starting from the outside, that would require only a little bit of energy because it's very far from uh, the nucleus and the attraction thereof. So you will see for all the elements A, B, C, and D, the first energy is it's in kilojoule per mole, and the numbers is low compared to the second energy, ionization energy, and the third one is even more, and the fourth one even more, and so forth. And the reason is, as you remove the first and then the second, and then the third, and then the second, and fourth, and then the fifth electron, you're getting closer to the nucleus. And the number of protons in the nucleus remains the same, and the number of electrons becomes less. So the force of attraction on the remaining electrons is very strong, and that's why the first to the fifth or the sixth or the eighth ionization energy will always increase. If you look at the pattern, you will see the third electron is removed, the fourth electron is moved, the fifth electron is moved. So therefore, these two can't both have 5 electrons only. So the D would have 6 electrons. Okay. So why do A only have a first, second, and third ionization energy? And the reason would be then there isn't a fourth and a fifth electron that can be removed. So this is an element, lithium, having only 3 electrons. B will be an element having 4, C 5, and then 6 will have, D would have at least 6 electrons. Give the valency of the elements B and C. B will be an element of, it will have 4 electrons, 2 in the first energy level, 2 in the next energy level, so it would be an element of group 2, and the elements of group 2 have a 2 plus charge. C has 5 valence electrons, so therefore it will have 2 in the first energy layer and 3 in the next energy layer. It will therefore have a charge of 3 plus, being an element of group 13. Right, then 4.1 says draw the alpha diagram of element C. So it will be, you have to make a provision for 5 electrons, 1 S, and in the little block 2 electrons pointing in opposite directions, representing the first 2 electrons. Then it moves over to 2s, next 2 electrons goes in there, and then in 2p only 1 electron, although you have 3 p orbitals there. At number 4.2, enter the electron configuration of element D. Element D will now have 6 valence electrons. It will look like this. So it would be 1s2, 2s2, 2p2. So you can see here, I've indicated here, and I can't see. To remove this electron would be your first energy level, second, third, fourth, and then you will see after 4 it becomes huge, 6,221, and then the next one 37,820, because now you are trying to remove this electron, and this electron is much closer to the attraction force of the nucleus on it. So you will have need a lot of energy to remove this one. And to remove this one would be maybe impossible, because you need an enormous amount of energy to remove the last one. Right. Lewis diagrams or dot diagrams. I always say, remember the dot of Lewis, only indicating valence electrons. X has 6 dots around it, so it's an element of group 16. Y has 7, so it's an element of group 17. Z has 5 around it, so it's an element of group 15. Question 2. In nature, the element X exists as a diatomic element. Draw a Lewis diagram for the binding. So the only diatomic element in group 6, group 16 is oxygen, which has the formula O2. So one oxygen atom has two paired sets of electrons and two unpaired electrons. So now the other one would look exactly the same, and they will overlap at two positions, and so we draw these 4 electrons in between the two, and then the two pairs of each atom at the top and where it was here. Okay, so these just go here to the middle, and they share these 4 electrons with each other. Right, then here we move on to what kind of bond occurs in question 2. It is O2, so it's two atoms which are both identical non-metallic atoms, so it's a covalent bond. Then it says if hydrogen connects to element Z, there is Z, 1, 2, 3, 4, 5, so it's a non-metal. Hydrogen has only each hydrogen atom 1 electron, so 3 hydrogen atoms will react with one of element Z, and it will then have the formula H3Z. And then the last one, the 3 steps of the forming of sodium chloride. Sodium is an element of group 1 and it's a metal, so it donates its 1 electron, and the ion forms a +1. The chlorine is an element of group 17 with 7 valence electrons, accepting the 1 electron donated by sodium. Now it has 8 dots around it and a -1 charge. The +1 and the -1 bonds, and now I have Na, and the fluorine remains. You can say NaCl, or you can say Na and then the Cl with its 8 electrons around it in the rectangular brackets, square brackets, rather, is then your final product. Here you have the balancing of a chemical reaction, but before we do that, make sure you get the names of the formula. The name, you know, the polyatomic radicals, like sulfate, which is SO2 minus, and so forth, hydroxide, OH minus, and so forth, and know how to write a formula. And then balancing of equations when hydrogen gas reacts with oxygen gas. Remember, they can only appear in nature as 2 diatomic gases, so they form water, and we all know water has the formula H2O. So then we have to balance, and when we balance, we count the number of each element must be equal to the number on the right hand side. I have 2 hydrogen atoms on the left hand side, 2 on the right hand side initially. I have 2 oxygen atoms, and I have 1 on the right side. So to balance it, I can just fill in the 2 in front of the H2O, but now the hydrogen becomes 2 times 2, which is 4, so I have to put a 2 in front there as well. Right, guys, this brings us now to the end. Thank you for attending this session. I thank you for really working well, for attending, and I wish you all the best, and I really wish that you will be performing very well in the coming exam. Goodbye.